Hello everyone, and welcome to our channel, MooTechie. It's wonderful to have you here as we dive into a fascinating topic that powers stars, helps doctors diagnose diseases, and even lets us peer back in time. Let's get started. Now, let's begin with an introduction to nuclear chemistry. This field studies the nucleus and the incredible reactions that happen within it. We'll focus on radioactivity, decay, and the immense energy involved. And you'll see its amazing applications everywhere, from medicine and industry to cutting-edge research. For a bit of visual context, imagine a simple diagram of an atom with a central nucleus and electrons whizzing around it. Moving forward, let's quickly revisit some atomic structure basics. The nucleus is the atom's core, holding protons, which have a positive charge, and neutrons, which have no charge. Electrons occupy shells or orbits around the nucleus. The atomic number, Z, equals the number of protons, while the mass number, A, equals the total number of protons and neutrons. So we have the proton, or P+, the neutron, or N0, and the electron, or E-. The nucleus is at the center, surrounded by those electron shells. A diagram here clearly labels the dense nucleus and the surrounding electron shells. Now, let's explore what isotopes are. Isotopes are atoms of the very same element, so they have the same atomic number, Z, meaning the same number of protons. But they have a different number of neutrons, N, which gives them a different mass. This means they have very similar chemical properties, but then have vastly different nuclear properties. Classic examples are carbon-12 and carbon-14. To compare these carbon isotopes, let's look at their details. For C12, the mass number A is 12. It has an atomic number Z of 6, meaning 6 protons, and it has 6 neutrons. For C14, the mass number A is 14. It also has 6 protons, but it has 8 neutrons. This side-by-side comparison really highlights how the neutron count changes everything. Next, we'll look at isotope notation. The standard format is the mass number A over the atomic number Z, followed by the element symbol, for example, 14/6C. Remember, A is the mass number, which is protons plus neutrons, and Z is the atomic number, which is just a number of protons. To find the number of neutrons, you simply calculate A minus Z. A diagram here shows this A over ZX notation, with callouts clearly pointing to the mass number, the atomic number, and how to find the number of neutrons. As we continue, let's understand stable isotopes. These have a balanced neutron-to-proton ratio, which results in a stable nucleus that doesn't change. They do not decay or emit any radiation. Examples include the common carbon-12 and oxygen-16. A simple atomic visual here indicates a balanced, happy, and stable nucleus. Coming up, we'll discuss their unstable counterparts, the radioisotopes. Unstable nuclei are always trying to become more stable, and they do this through a process called radioactive decay. In the process, they emit radiation like alpha, beta, or gamma particles. Familiar examples include C14, which is radiocarbon, and U-238, uranium. An icon here represents this emission of energy and particles from an agitated, unstable nucleus. So what does this radioactive decay look like? Let's break down the types. Alpha decay, or alpha radiation, consists of 2 protons and 2 neutrons. It has very low penetration power and can be stopped by something as simple as a sheet of paper. Beta decay, or beta radiation, involves the emission of an electron or a positron. It has moderate penetration and can be stopped by a sheet of aluminum. Gamma decay is the emission of a high-energy photon. It has very high penetration power and requires dense materials like lead to attenuate it. A diagram shows a radiation source, with alpha being stopped by paper, beta by aluminum, and only lead blocking the powerful gamma rays. The key takeaway is that penetration power increases from alpha to beta to gamma. This leads us to a crucial concept: half-life. The half-life is the time it takes for the radioactive activity of a sample to drop by 50% for a given nuclide. It follows a predictable exponential decay pattern, and it's completely independent of how much material you start with. This concept is fundamental for determining safe dosage levels in medicine and for overall radiation safety. A graph plots relative activity against time and half-lives. It starts at 1, drops to 0.8 after one half-life, then to 0.5, then 0.3, and so on, visually showing how the activity halves at each successive half-life. Now let's see how this is applied in the real world, starting with medical applications. In PET and SPECT imaging, tracer isotopes like fluorine-18 and technetium-99 are used to visualize how organs are functioning inside the body. In radiotherapy, targeted isotopes like iodine-131 and lutetium-177 are used to deliver therapeutic radiation directly to cancer cells. And radioisotopes are also used for sterilization of medical devices and as tracers in metabolic diagnostics. The applications extend beyond medicine into the industrial world. For thickness gauging, radioactive sources are used to monitor the thickness of materials like sheets and films during production. In industrial radiography, gamma sources are used to take images of welds and castings, revealing hidden defects just like an X-ray. And for leak detection and process tracing, radioisotope tracers are injected into systems to track flows and pinpoint the exact location of leaks. Scientific research also relies heavily on isotopes. Radiocarbon dating is a famous technique that uses the predictable decay of carbon-14 to determine the age of ancient artifacts. Tracer studies use radioisotopes to track pathways and mechanisms in biological and chemical processes. And environmental and forensic science uses isotopic signatures to trace pollution sources, study environmental cycles, and determine the provenance of materials. So let's summarize the key takeaways. Isotopes are atoms of the same element, with the same number of protons but different numbers of neutrons. We have stable isotopes and radioactive isotopes, a distinction determined by the neutron-to-proton ratio in the nucleus. The concept of half-life underpins all uses and safety protocols, as it allows us to predict decay and guide dosage. And the broad impact of nuclear chemistry is undeniable, providing essential tools for medical imaging, industrial quality control, and scientific tracing. Thank you for joining this exploration of nuclear chemistry. We hope you found it enlightening. Thank you. See you in the next class.